Last chapter, water and hydrogen. Now, water is the most abundant substance on Earth. About 71% of the planet Earth is covered with water. It is found in water bodies such as seas, oceans, lakes, rivers, and underground sources. It is also a major component of the living cells of organisms. It is a compound of 2 hydrogen atoms and 1 oxygen atom. Water is also a product of a vast majority of reactions. Now let's perform an experiment to determine what products are formed when a candle burns in air. We place a funnel above a burning candle and connect it to a U-shaped tube dipped into ice-cold water to allow for condensation. This U-shaped tube is connected to a test tube with lime water. The test tube is then connected to a suction pump. And as you can see, the lime water is already forming a white precipitate indicating the presence of carbon dioxide. Candle wax belongs to a group of carbon compounds called hydrocarbons. They burn in air to produce water and carbon dioxide. There are 2 common methods of testing for water. These methods only test for the presence of water and not its purity. The first method involves the use of anhydrous copper 2 sulfate, which is a white solid. The term anhydrous means without water. In the presence of water, it becomes hydrated copper 2 sulfate, which is blue in color. Hydrated means with water. Another method is by using cobalt 2 chloride paper, which turns from light blue to pink in the presence of water. The test applies the same concept as in the anhydrous copper 2 sulfate. The anhydrous form of cobalt 2 chloride is light blue, while the hydrated form is pink. In summary, anhydrous copper 2 sulfate and anhydrous cobalt 2 chloride are used to test for the presence of water. The change is from white to blue for copper 2 sulfate and from blue to pink for cobalt 2 chloride. Physically, pure water is a colorless, odorless, and tasteless liquid at room temperature. It boils at 100 degrees Celsius and freezes at 0 degrees Celsius at sea level. Water has a density of 1,000 kilograms per cubic meter and has a very high heat capacity. It is polar and therefore dissolves only polar substances. Chemical properties of water. We start with reactions with metals. Now, different metals react at different rates with water. Let us compare the reactions of water with these metals: tin, iron, magnesium, copper, zinc, and calcium. We also want to test for the acid-base properties of the product, so we need an indicator. We first add a few drops of phenolphthalein indicator in the water. It is colorless in neutral solutions. Then we shall pour the water into the test tubes containing our metal samples. Tin, iron, magnesium, copper, zinc, and calcium. The reaction is already evident in calcium. The solution turns pink, indicating it's alkaline. Magnesium is also showing some signs of a reaction. For the others, nothing much can be seen. Generally, Metals react with water to form alkaline metal hydroxides and hydrogen gas. Reactive metals such as lithium, sodium, and potassium react more vigorously with water. Here we have 3 beakers containing water that has been added phenolphthalein indicator. We start with lithium metal. The metal reacts vigorously with water, producing a hissing sound, and some fumes can be seen. The solution turns pink, indicating it's alkaline. Let's now see sodium. You see it darts on the surface with more intensity, and some sparks can be seen from time to time. The fumes are more, and the solution turns pink as well. Lastly, potassium. We expect it to be more reactive than sodium, and for sure, it spontaneously ignites a flame when inserted in water. It is actually explosive. This is because the reaction generates a lot of heat that ignites the hydrogen being generated. Again, the solution turns pink. The reactions are represented by these equations. Reactions of metals with steam. We saw that magnesium reacted quite slowly with cold water. Let's see what happens when steam is passed over a heated magnesium ribbon. So we have a magnesium ribbon in a boiling tube. At the base, we have cotton wool soaked with water. First, we heat the magnesium ribbon until it starts to glow. Then we heat the cotton wool to produce steam. You see the open end ignites when a flame is introduced. This is because magnesium reacts with steam to form magnesium oxide and hydrogen gas. The gas is ignited at that end. Zinc and iron can also react with steam to form oxides and hydrogen gas. Next, we look at hydrogen. Hydrogen is a colorless, odorless gas at room temperature. It is the first and the lightest element on the periodic table. It does not exist freely as an atom. 2 hydrogen atoms combine to form a diatomic molecule of hydrogen gas. It is found in the sun and most stars, and the giant planets like Jupiter are composed mostly of hydrogen. On Earth, it is found in compounds such as water, fossil fuels, and living organisms, but very little as free hydrogen gas. When metals react with acids, they actually displace the hydrogen in the acid to form hydrogen gas. So metals which are above hydrogen in the reactivity series normally react with acids to form salt and hydrogen, like zinc. Metals below hydrogen in the reactivity series do not displace hydrogen in acids. Most reactive metals will displace hydrogen in water, for example, sodium. You can test for the presence of hydrogen by placing a burning splint at the mouth of a vessel containing hydrogen gas. You should hear a very distinctive squeak pop sound, which confirms the presence of hydrogen gas. Hydrogen gas is prepared in the laboratory by reaction of zinc granules and dilute hydrochloric acid or sulfuric acid. The apparatus setup is as shown here. The zinc granules are taken into a Wool's bottle. dilute sulfuric acid is added to the granules through the Thissell funnel. A reaction takes place and hydrogen gas is liberated. The gas is collected in the jar by downward displacement of water. Metals react with dilute acids to form salt and hydrogen. Sodium and potassium should not be used because the reaction will be explosive. Magnesium can be used, but it's expensive. We use zinc granules instead of zinc metal to increase the surface area for reaction. Aluminium reacts slowly with acids due to a layer of aluminium oxide on its surface. Calcium cannot be used with sulfuric acid because the salt formed, calcium sulfate, is insoluble and forms a coat on the metal surface, preventing further reactions. Physically, hydrogen is a colorless and odorless gas at room temperature. It is insoluble in water and it's less dense than air. Chemical properties, combustion. Now, in this experiment, we prepare hydrogen gas by reacting zinc granules with sulfuric acid. The gas evolved is passed through a U-shaped tube containing calcium chloride, which absorbs the moisture present in the gas, making it dry. When ignited, pure hydrogen burns quietly with a blue flame. We then arrange a setup for circulating cold water and bring the flame near the cold water. You will see that some water droplets collect on the outer surface of the flask. Thus, hydrogen burns in air to form water as the only product. Pop sound is produced when a mixture of air and hydrogen is ignited. Otherwise, pure hydrogen burns quietly. Reducing properties of hydrogen. Now, we said that a more reactive element will displace a less reactive one from the latter's compound. Hydrogen is no exception. It will displace metals below it in the reactivity series from their compounds, for example, copper. For instance, consider this brown copper solid in a china dish. We heat the china dish with copper. The copper powder turns from reddish brown to black. This is copper 2 oxide. Copper combined with the atmospheric oxygen to form copper 2 oxide. Therefore, copper is oxidized to copper 2 oxide. If hydrogen gas is passed over the hot copper 2 oxide, the powder turns brown due to formation of copper. Hydrogen displaces copper from its oxide. This is called reduction. In the process, hydrogen itself is oxidized to water. Because both oxidation of hydrogen and reduction of copper 2 oxide occur simultaneously, this is called an oxidation-reduction reaction. So hydrogen is a reducing agent, while copper 2 oxide is the oxidizing agent in this case. Finally, the uses of hydrogen. In the chemical industry, hydrogen is used to make ammonia for agricultural fertilizers in the Haber process and to make hexane methanol, which are needed to make plastics and pharmaceuticals. It is also used to remove sulfur from fuels during oil refining process, where it forms the awful-smelling hydrogen sulfide. Large amounts of hydrogen are used to hydrogenate vegetable oils to form fats, like to make margarine. Because it's lighter than air, it is used in balloons, which make them rise. Actually, its low density made it the choice for one of its first practical usage, filling airships. But this ended when the Edinburgh ship caught fire on the 6th of May, 1937. If we compare coal, oil, natural gas, and hydrogen as fuels, you can see that when they combine with oxygen, coal and crude oil produce the most carbon dioxide. So using natural gas in place of coal and oil does help to reduce carbon dioxide emissions. Hydrogen, which only forms water when it burns, could be the clean fuel for the future, but the hydrogen must be generated from water using replenishable energy.
Now let's talk about one of the most Hollywood-loved ancient civilizations, the Romans. Sure, from a chemistry perspective, the Romans were big time. They invented coinage of all kinds, thanks to the Greek knowledge, concrete and cement to name a few, but their biggest chemistry conquest? Plumbing. Specifically, indoor plumbing. The Romans crafted pipes out of lead metal, which doesn't occur naturally on its own. So you really have to know your chemistry to extract it from rocks, and the Romans did. They were also the first to seal pipes in concrete to help deal with water pressure and bursting pipes. All of these accomplishments happened over about 4,500 years, a mere blip on the evolutionary radar. From melting copper pins to crafting lead pipes, the civilizations we still talk about thousands of years later left their mark with metal. And those metals were forged, formed, and reshaped with chemistry.